4.3.1 Simple Harmonic Motion. The periodic nature of trigonometric functions is useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by a wave motion. The motion of this nature can be described by a sine or cosine function and is called simple harmonic motion. The wave shape of the graphs of the function is called a sinusoid, and the function is called a sinusoidal function. So we have our two equations, our general equations for sine and cosine up here. So just recall that the A value is the amplitude and the D value is the midline, and we have our two equations to find the amplitude, max minus min divided by 2 and max plus min divided by 2. Remember that the B value is called the frequency, so it's the number of cycles from 0 to 2 pi. Your period of your graph is going to be 2 pi divided by your B value. Your key point to find by taking the period of your function divided by 4, and then of course that C value is the phase shift, so how we've moved left and right on our graph. Looking at this first example, it says, as you ride the Ferris wheel, your distance from the ground varies sinusoidally with time. When the last seat is filled and the Ferris wheel starts, your seat is at the position shown in the diagram. Let t be the number of minutes that have elapsed since the Ferris wheel started. It takes you 12 minutes to make one revolution. The diameter of the wheel is 55 feet. When you begin, your seat is 5 feet from the ground. So the first question asks us what's the period, which we just underlined. So we know it takes 12 minutes to make one revolution. So the period would be 12 minutes. And then it says, what's the amplitude? So remember, the amplitude is going to be your maximum minus your minimum divided by 2. So we need to figure out what the max is at. So if the diameter of the wheel is 55, and I know I'm 5 feet off the ground, so that means the maximum is going to be at 60 feet. And the minimum would be at 5 feet. So the amplitude is going to be 60 minus 5 divided by 2, which is 55 over 2, or 27.5 feet. Then it says, what is the vertical shift? So remember, the vertical shift is your D value, which is your maximum minus your minimum divided by 2. So in this case, plus your minimum divided by 2, so 65 divided by 2, which is 32.5 feet. Next, we want to sketch a graph. So in order to sketch a graph, we need to figure out a couple more things because we need to know what our key points are going by on our graph. So if we know that the period is equal to 12 minutes, then I know my key points. You take the period, which is 12, and divide it in 4 equal parts. So we know that our key points are going by intervals of 3 minutes. And then eventually we'll need to figure out the B values. We'll do that in just a minute. So first I want to sketch a graph. And on my graph, I know I have my maximum, which is at 60. I have my vertical shift at 32.5, and I have my lowest, which is 5 feet above the ground. So from 0, because we're starting here at the bottom at time equals 0, so then our next key point would be 3, 6, 9, and 12 makes one full wavelength. So then for this, I know that I am starting at time equals 0 at the bottom, so at 5 feet. After 3 minutes, now I'm at my midline, which is at 32.5 feet. At 6 minutes, I've reached the top of the Ferris wheel. At 9, I'm back at my midline. And then at 12, I'm at 5 feet. So then that would make it all the way around my Ferris wheel. My graph looks something like this. And of course, I like to always draw the midline there. And so it says to write an equation for this. So in order to write an equation, we know we need our B value. And if, of course, we have a phase shift, we can put that in as well. So for this, my B value, remember, we know that the B value times the period is equal to 2 pi. So that's the equation we use to find the period and our B value depending on the information that's given to us. So for this, that means that the B value is equal to 2 pi over my period. So 2 pi divided by 12 is equal to pi over 6, and we're going to need that for our equation. It looks like since our graph is starting down here on the y-axis, that tells me this is going to be a cosine function. So we can use y is equal to, and because it's starting down, that means my amplitude needs to be negative. So negative 27.5 times the cosine, and then my b value is pi over 6. In this case, if we're starting the y-axis, we don't have a phase shift, so x, and then plus my vertical shift, which is 32.5 feet. So this is one particular equation you get. Of course, we don't have to use this point down here. We could have made it of this point right here and had a phase shift. So I could have also done y is equal to negative 27.5 times the cosine of pi over 6 times x minus 6 plus 32.5. So our phase shift in this case would be 6. We can also make a sine graph out of this if we start on our midline here, or we could start here. So if I start at this one right here, I would get y is equal to, and it's going up first, so it's positive. And I'm sorry, this last graph, because it's starting up at the top, it should have been positive as well for the amplitude. So 27.5 times the sine of pi over 6 times x, and then now you can see that our graph shifted right 3, so minus 3 plus 32.5. And of course we have other equations that we could come up with as well. So the next part says that we want to predict the height above the ground when the time is equal to 9. So that means I'm just plugging 9 in for x into one of these equations. So we'll use the first equation since that's the easiest. So y is equal to negative 27.5 times the cosine of pi over 6 times 9 plus 32.5. When you're doing this in your calculator, make sure you are in radian mode. If you're not in radian mode, then you're going to get all of these problems wrong, so just be careful with that. So if we go to our calculator now, we can plug that into our graphing calculator. So we have 27.5 times the cosine of, and oops, it's negative 27.5, so I need that negative in front. Negative 27.5 times cosine of parentheses pi divided by 6 times 9 plus 32.5, and make sure I'm in radian mode, which I am, and then enter. So I get 32.5 feet. So if I go back, I know that when t is equal to 9, my y value is 32.5 feet. And really, we didn't need to plug that into our calculator because we could have looked at our graph. It's actually one of our key points. So you can see right here that when we plugged it in, our equation is correct because we got our 32.5 feet above the ground. So for the next example, it says, suppose that a weight is hanging from a spring is set in motion by a push upwards. It takes 5 seconds for it to complete one cycle, moving from its equilibrium position, so we're starting at the equilibrium, to 8 centimeters above, then dropping 8 centimeters below, and returning to its equilibrium position. Of course, this is an idealized situation, which the spring has perfect elasticity and friction and air resistance, etc. So we're not thinking about any of that for this problem here. So it says sketch a picture of the path of the weight. So the first thing we want to do is start to think about all the different things we have in our equation and what we need for our equation. So if I start to draw a picture, the x-axis is going to be my equilibrium. And for this, we're going 8 centimeters above and 8 below our equilibrium. So that tells me my max is going to be 8 and my minimum is going to be negative 8. You have to be careful on these weight problems because you have to read where it's starting at. Sometimes you start above the equilibrium, sometimes you're starting downwards and putting pushed upwards. So make sure you read carefully. So then for this, we know that our amplitude is our maximum minus our minimum divided by 2, so that gives us 8. Our vertical shift is our maximum plus our minimum divided by 2, which is 0. And then our period of the function, it told us it takes 5 seconds to complete one cycle. So the period is 5, which means then your key points are going by 5 divided by 4, which is 1.25. So on my graph, I'm starting at time 0 here on the y-axis, and then at 1.25 seconds, I get my first key point. The next one, we're adding another 1.25 to get 2.5. Add another 1.25 and I get 3.75. Add another 1.25 and I end at 5, which is the first cycle of my graph. So then again, for this graph, we are starting at the equilibrium, then going 8 centimeters above, back to the equilibrium, and 8 below. So this is what my graph would look like. Now we want to find the equation that models this movement. So if I look on my graph, I don't have a phase shift if I start right here at the y-axis at 0. And since my midline is right here, I know this is going to be a sine function. So y is equal to, the amplitude is going to be positive because the graph is going upwards first. So y is equal to 8 times the sine of, I need to figure out my b value. So remember that your b value is equal to 2 pi divided by the period, which is 5. So 2 pi over 5. And then there is no phase shift, so x, and then plus 0 because there's no midline, but you don't really need that plus 0 there. So we can just say that this is our equation. Of course, we could have came up with a sine equation starting here and then had a negative amplitude, or here. We could also come up with a cosine equation. So if I did a cosine equation, I would start at the top here. So y is equal to, and since it's at the top, we don't need a reflection, so 8 times the cosine of my b value, which is 2 pi over 5. And then in this case, we do have a phase shift. It'd be x minus 1.25 and then plus 0. So this is another equation. You don't really need to write 2. We're just practicing with our different phase shifts that we have right now so you guys can see. Then it says use your function to predict the height of the weight after 3 seconds. So that, of course, is when x is equal to 3. We want to predict what the height is going to be. So that means I'm just plugging 3 in for x into my equation. And of course, you can just use your calculator to go ahead and do that. So when you plug that into your calculator, again, make sure you're in radian mode, and you will end up with negative 4.7 feet. Since it's negative 4.7 feet, that means we're 4.7 feet below the equilibrium. And then you can kind of check on your graph to see if that makes sense. So if you look around here, this is where about 3, in this case, seconds would be. And if you look, you're at a negative value, so that makes sense. Then it says in the first 5 seconds, when will the height be 6 centimeters below the equilibrium position? So for 6 centimeters below the equilibrium position, that means it would be negative 6 is equal to 8 times the sine of 2 pi over 5x. So of course we're solving for x. So the best way to do this problem would be to plug this into your calculator. You can plug this into y1 and y2, and then we're going to look at the intersection between the two. So in our calculator, we want to go to our y equals and put in the equation 8 sine 2 pi over 5 x, and then make sure you always put your fractions in parentheses, just a good habit to get into. And then in my y2, I'm going to put negative 6 because we're looking at the weights being 6 centimeters below the equilibrium point. So if I go ahead and hit graph, this is what my graph looks like. This, we don't really need this big of a window because we're only looking at in the first 5 seconds. So I'm just going to change my window real quick. So I'm looking at 0 to, let's do 6 seconds, and then hit graph. So now I can see within the first 5 seconds, which would be here, that it hits twice in one wavelength. So I have to go to second trace, and we're looking for the intersection to find their x values. So I can use my left and right arrows to go over to where that is. So the first curve, you just hit enter. Now you can see if I hit my left and right, I'm on my second curve. So just enter again, and then enter for guess. And we get 3.71 seconds for the first answer, and then our second answer we have to do again, second trace, number 5, which is the intersection. Now we need to scroll over to the other side. Oops. Ah. So scroll over to the other side. And hit enter. And we get 4.32 or 4.33. So if I go back, go ahead and write that down. So we get x is equal to 3.17 seconds, and x is equal to 4.33. Okay, so now let's go ahead and look at the next problem that we have. So we're going to do example 3, which is modeling trigonometric data, again, for something that has to deal with temperature and the weather. So this says the following table shows the average monthly temperature in Cleveland, Ohio, based on the data from 1971 to 2000. Since average temperatures are not likely to vary much from year to year, the data essentially repeats itself the same pattern in subsequent years. So a periodic model is appropriate. First, we're going to make a scatter plot of the data. So I'm just going to pause this to make the scatter plot first. So I made a scatter plot of my data, and I highlighted the minimum and the maximum value in my table. So for this, it says find a sinusoidal function that models the temperature by hand. So for this, first we need to figure out what the amplitude is. So the amplitude, remember, is your maximum, which is 71.9, minus your minimum, 25.7. Divide that by 2, and we get 23.1. Your midline is your maximum plus your minimum divided by 2, which gives us 48.8. And for this, the period of my graph, because we're talking about the months, is going to be 12 months. And so the key points would be equal to 12 divided by 4, which is 3. We don't need that right now, just quite yet, but we do need the b value. So remember, the b value is equal to 2 pi divided by the period, which is 12, so pi over 6. And now we can use that to help write our equation. So for this, if I think about my midline being at 48.8, that would be somewhere in between 45 and 50, so somewhere in here. So if I look at that, I can see my minimum, we said, was at January, and my maximum in July, so up here. So I'm going to start with a cosine graph because I can use a phase shift of 1. So that would be negative because it's starting down here. So y is equal to negative my amplitude, which is 23.1, times the cosine of my b value, which is pi over 6. And then because my minimum is starting at January, so a phase shift of x minus 1, plus my midline, which is 48.8. So this would be one possible equation that I could use. And then if I think about my key points being 3, so if I have a minimum at 1 and I add 3 to that, so 1 plus 3 would give me 4. So my next key point would hit here on my graph. So if I would actually draw this in, and make a curve. It won't fit the data exactly, but it'll be close to it. So I would get y is equal to, and if we're starting here, it'd be a positive sine graph. So amplitude would be positive 23.1 times the sine of pi over 6 times x minus 4, because we'd have to move a graph to the right 4, plus 48.8. Of course, there are other possible answers that we could have, but these are just 2 of them. So these are the equations we get by hand. Now we can also make a scatter plot on our calculator and use the sign regression to help us figure out what the data is going to be. So let's go ahead and do that. So next you want to go to your calculator. Of course, we're making a scatter plot. So go to Stat and enter on Edit. And you're going to enter your months into list 1 and the temperatures into list 2. So now I've plugged them into list 1 and list 2, and I always like to check over my values to make sure I didn't enter something incorrectly into the calculator. So after you do that, then remember to come up with the equations. You can go to Stat, and now we're calculating. And if you scroll down, you will see at the bottom for right here, you get sign regression. So that's what we're calculating. So I'm going to hit enter on that. So for iterations, I'm just going to leave it at 3. So we're in list 1 and list 2. Don't worry about the period right now. So then we're going to store this regression equation into our y equals. So remember to do that. You go to vars, which stands for variables, y vars, which is y variables, enter on function, and I'm going to put it into my y1 and hit enter. Now, when you're doing your sign regression in your calculator, notice that the equation's a little differently than what we have because they didn't factor out the b value here, so they leave it in there. So that it means our phase shift looks a little bit different, so we would actually have to factor out the b to see how closely it matches what we have. But now I can go ahead and write this equation down on my paper. So now I just wrote down my equation from what I got in my calculator, and I wanted to check what the period was according to my calculator. So 2 pi divided by b, which is 2 pi divided by 0.5018 gives us the period, which is about 12.52. So this, notice that our calculator is making it so that we're trying to hit as most data points as we possibly can as we're making our sinusoidal function. So just kind of look at this, we know that our equation probably is a little bit more accurate because we're actually using a period of 12 versus the calculator that's making the period into 12.52. Now, of course, the reason I didn't put in when we were calculating the equation, the period to be 12 is because some of the older calculators don't do that. So then rather than putting in to make it so that we have the same thing, that's why I just left it as nothing. So for this, if I wanted to actually look at my graphing calculator, remember I can look at the graph and hit zoom 9 on here for the scatter plot. Oops, and I got to turn on this dot plot first. So if I go to my y equals, or second y equals, got to turn that stat plot on. So then hits zoom 9, and there's my graph, and this is the calculator equation that they came up with. So it looks like it's a pretty good fit. We could also put our equation in just to check it if we wanted to as well. Ours might be a little bit different, like I said, because we did it by hand. But as you can see, by hand or using your calculator will give you two good equations. So for this, we can see that the period is different. That's how they different from one another. And also the phase shift was different. It was not factored out here. So the period and the phase shift. So then it says use the calculator model to predict the times of year in which the average temperature is 45 degrees Fahrenheit. So that's why I wanted to look at the scatter plot on my calculator. So looking at this, if I want to predict when it's 45 degrees Fahrenheit, I would want to go to my Y2 now and plug in 45 and hit graph. And then, of course, I needed that other equation in my y equals so that I can look at the intersection. So if you don't have that other equation, your y equals, you would want to make sure that you put that in there. So now I can go to second trace and do the intersection and scroll to close to the point of intersection and just hit enter twice or 3 times, sorry. So we get about 3.7. So that right there would be the first point. And if I do it again, second trace intersection and go to the other side. And then I'm going to hit enter 3 times. I get about 10.6. So now I can see that from my graph, I just made it a little bit bigger right here. So we have late March and October are the times in year where the average temperature is around 45 degrees Fahrenheit, which makes sense for Ohio. So let's go ahead and look at the last example that we have, example 4. So this one says a Ferris wheel as you ride, Ferris wheel problem, as you ride the Ferris wheel, your distance from the ground varies sinusoidally with time. When the last seat is filled and the Ferris wheel starts, the seat is at the position shown in the figure, which is right here. So notice that's not at one of our key points because it's not here on our graph, or up here. Let t be the number of seconds that have elapsed since the Ferris wheel started. You find that it takes 3 seconds to reach the top, 43 feet above ground, and that the wheel makes 1 revolution every 8 seconds, and the diameter of the wheel is 40 feet. So that's the important information that we need from our problem. So let's go ahead and kind of look at this. So for this problem, if we want to start to look at everything, we would probably first want to figure out what the maximum and the minimum is, because that helps us figure out our amplitude and our vertical shift. So the maximum, we know it told us, is 43 degrees above ground, so 43. And the minimum, if the diameter of the wheel is 40, so that's 20 here and 20 here, so that is 43 feet above the ground. That means there's 3 feet is where our Ferris wheel is above the ground. So minimum is 3 feet, which means our amplitude is equal to our maximum minus our minimum divided by 2. So that gives us 20. And our vertical shift would be our maximum plus our minimum divided by 2, which gives us 23. And then the period is 8 seconds. Of course, this is a very fast Ferris wheel. If we're at the top after 3 seconds, and it takes 8 seconds to go around with a diameter of 43. And then for this, our b value would be equal to the period 2 pi divided by the period, which is 8, so pi over 4. And our key points go from the period, so 8 divided by 4, which is 2. And now let's go ahead and just sketch the graph of this. So if I think about my graph, again, this one is a little bit different, so you kind of have to be careful, because at time 0, we don't really know where we're on the Ferris wheel. So I'm going to go ahead and draw the 3 feet, and then the midline is at 23, and then the tallest is 43. So we know that 3 seconds we're at the highest height. And then our key points are going by 2, so I'm going to add 2 each time. So that'd be 5, 7, 9, and 11. So remember, the period is 8. So if we do 11 minus 3, we get 8. So the distance from here to here is going to be 1 wavelength. So the next key point would be here. At 5 seconds, we have a height of 23 feet. At 7, 3. 9 would be 23, and 11 at 43, back at the highest. So here's what the graph looks like. So I can go ahead and just from this make my equations, and it looks like if we start up here, we have a cosine graph because my midline, of course, is at 23. So if I start at this point, I can make an equation y is equal to the amplitude, which is 20, times the cosine of my b value, which we said was pi over 4, times x minus 3, plus my vertical shift, which is 23. So that would be one equation. I could also make a equation from sine starting here with a phase shift. So y is equal to, and it's going down, so we need a negative amplitude. So negative 20 times the sine of pi over 4 times x minus, in this case, 5 plus 23. And for this, like I said, you have to be careful because think about your key points. If they're going by 2, so then my next key point would be here at 1, and at 1 we would be at our midline, and then the next key point after that would be 1 minus 2 would give us negative 1, so that would be down here. So notice that at time equals 0, we don't really know what height we're at, but we can figure that out by plugging in 0 into our equation and finding where the height is. So we'll do this in just a second. So I went to my calculator and I cleared out what we had before and I typed in the equation. So 20 cosine pi over 4, make sure you put that in parentheses, and then another parentheses, x minus 3, and then close your parentheses twice, plus 23. I had to turn my stat plot off, so I went up here and hit enter and made sure that was off for the last one. And then remember, we changed our window. So because we changed our window, I had to change my window again. And I've noticed I'm going to do values from negative 2 to 12 in my y equals. So negative 2 to 12, sorry, for x equals, and my y equals would be from 0 to, I did 45, so it's a little bit above that. So if I hit graph, now I can see what my graph looks like. And then I can go to second trace value, which is number 1, and I can hit x equals 0, enter, and notice that at time 0, I'm at 8.8 or 8.9 feet. So again, that's why you can't assume that you know where you're starting at time 0. So that's why we had to start with the information given, which again was at 3 seconds. We were at the top at 43. So because that's at time equals 0, we were at 8.9 feet. So then it says for this, predict your height above the ground when t is equal to 6. So then for this, when t is equal to 6, I can just go to my graph again and hit second trace and then do the value 1, enter, oops, second trace 1, and then I can put 6 and enter, and I get about the same thing. So at that value, I'm at the same height of basically it was at time 0. So 8.857 or 8.9 for this, for that at c equals 6. So bring this with you to class, and we're going to do some more practice problems looking at the sinusoidal function. So as you can see, it does start to get a little bit harder. We have to be careful of the wording because now with some of these sinusoidal graphs, we'll have, like this Ferris wheel problem, we have a phase shift. Whereas if we go back to looking at the first couple ones that we did, we at time 0, we're actually starting on the y-axis because it told us that we were starting on one of our equilibrium points here, or up here we were starting at our lowest point on our Ferris wheel. So we'll do some more practice, like I said, in class.